Good morning, everyone. I am Pratiti Dash, a fourth year student from the Department of Electronics and Communication Engineering. Today, I will be presenting our project titled Automatic Plant Watering System using Arduino. My fellow teammates are Devnita Shaha, Poshani Chakraborty, and Shomodeep Bhattacharjee. This project is a small but meaningful step toward creating smarter, more sustainable homes and farms using embedded electronics. During my IoT-based internship, I had the opportunity to explore the field of smart technologies and connected systems. I gained hands on experience in designing and implementing IoT solutions that involve the integration of sensors, microcontrollers, and cloud platforms. Using the Blink IoT app, I develop projects that monitor temperature data in real time and controlled LED indicators based on sensor readings. This experience enhanced my programming skills in C and embedded C and deepened my understanding of how hardware and software interact to create efficient real-time embedded systems. Before diving into the technical aspects, it is important to recognize the real world issue that the project aims to address. In today's fast paced lifestyle, many individuals enjoy maintaining indoor plants or small gardens but often struggle to water them consistently. Irregular or small gardens but often struggle to irregular watering, whether overwatering or underwatering, leads to serious consequences such as root rot, fungal growth, or dehydration of the plants. These inconsistent watering habits negatively impact plant health and growth, sometimes even causing the plants to die. Though this may appear to be a simple problem, it is one of that affects almost every plant owner, whether at home, in offices, or in greenhouse environments. The objective of this project is designed to design and develop an automatic plant watering system using Arduino and sensors to automate the irrigation process and ensure efficient water management. This system continuously monitors the soil moisture level and automatically activates a water pump whenever the soil becomes dry. Once the desired moisture level is achieved, the pump is turned off, thereby maintaining an ideal environment for healthy plant growth. In addition to improving efficiency, this project highlights the potential of automation and embedded systems in addressing everyday challenges. By integrating simple hardware components with intelligent control logic, it provides a sustainable, cost effective, and practical solution for plant maintenance. Overall, the system demonstrates how technology can be used to promote resource conservation, environmental sustainability, and smart agriculture practices. Now, I would like to hand over the presentation to Shomodi Bhattacharjee.
Thank you, Pratiti. So let's dedicate some serious time to the foundation of our project, the hardware components. Every successful system begins with selecting the right parts, and understanding their individual roles is crucial to troubleshooting and scaling these designs. At the absolute core, we have the Arduino Uno microcontroller. It is the central processing unit, the brain, responsible for executing our code and managing the entire cycle. Why we use Uno? Because it is a beginner friendly, widely documented, and robust enough for this application. It gives us the necessary analog input pins to read our sensors and digital output pins to control the pump. Its job is continuous. It waits for input, processes it, and provides output. Next is the system sensory input, the soil moisture sensor. This is where we bridge the digital world with the natural world. The sensor works by using two probes to measure the electrical resistance of the soil. When the soil is dry, resistance is high, and The sensor sends a high analog value to the Arduino. When the soil is wet, resistance is low and the value drops. The reliability of our system depends entirely on the accuracy and proper placement of this sensor, which must be buried deep enough to measure the root zone moisture, not just the surface. The output component, the pump, water pump, it is the muscle. It is a simple DC motor designed to push water from a reservoir through a tube and onto the plant. When selecting this, we considered its flow rate. It needs to deliver enough water quickly without flooding the pot. This is a critical factor when we talk about calibration, determining exactly how many seconds the pump needs to run to achieve the ideal moisture level. Finally, we address the critical interface between the low power Arduino and the high power pump. The Arduino operates on about 5 volt and very little current. The pump requires more power. If we connect the pump directly, we would fry the Arduino. So we use NPN transistor by acting as a switch. A tiny current from the Arduino's digital output pin, the base of the transistor, controls a much larger current flow to the pump from the collector to the emitter. This isolates the high power circuit from the sensitive microcontroller, protecting our main component. Moving from a component list to a functional system requires a clear plan, which is our circuit diagram. This diagram is essentially the blueprint that guides the physical wiring and ensures proper signal flow. Let's trace the connections and understand the logic behind them. Focusing on the input side first, the soil moisture sensor is wired to provide an analog voltage to one of the analog input pins on the Arduino, usually A0, which is an analog pin. Why we use analog pin? Because soil moisture is not just wet or dry. It exists on a spectrum. And the analog pin reads the voltage from the soil moisture sensor, then give it to the Arduino, and then it converts into a number between 0, which is very wet, and 1023, which is very dry, giving us the detailed data we need for precise control. Now, the output side, which is more complex due to the transistor, the water pump forms one part of a separate power loop. The transistor is intermediary. The digital output pins on the Arduino connects the base of the transistor. The digital signal is what controls the switch. When the Arduino sends a high signal 5 volt, it activates the transistor, completing the separate circuit that powers the pump. Finally, we have the LED indicator. This is the connected to another digital output pin, often wired in parallel to the pump signal. The primary function of the LED is feedback. In a real world application, the user needs to know the system is active or not. When the LED lights up, it confirms that the pump is currently running. We use a resistor in series with the LED to limit the current, preventing the LED from burning out and protecting the Arduino pin. Understanding this diagram is fundamental. It moves our project from a concept to a reliable, electrically sound circuit. We now arrived in the working principle. This is the software logic that defines automatic nature of our system. To make this clear, let's use the powerful and easy to understand analogy of human thirst. Think of our plant as a human being. A person senses thirst when their mouth and throat feel dry in our system. The soil moisture sensor is the mouth. It constantly monitors the environment and sends a reading the dryness level to the brain. The Arduino Uno is the brain. It receives the sensor reading the dryness signal and compares it to the preset threshold, which in our analogy is the actual feeling of thirst. This threshold is the line we have programmed. If the dryness level is greater than 600, the brain registers thirst. This is the critical if statement in our code. If the brain decides I am thirsty, it signals the water pump, which is the hand and arm, commanded to lift the glass. The pump turns on. Crucially, the pump does not run indefinitely. We have programmed it for a short controlled duration, a measured sip of say 5 seconds. This is the most important part of the automation. We avoid overwatering. We take a sip, not drink the entire jug at once. This action satisfies the immediate need while conserving water. After the watering is complete, the system enters a sleep period, a rest period of can say, of maybe 30 minutes to an hour. This pause is essential to allow the new water to diffuse fully through the soil before the sensor takes it to next reading. This cycle then repeats, ensuring the plant is never neglected and its thirst is quenched immediately and efficiently, all without human intervention. So we have made a simulation video where we can show you that how our system or how you can see this is the code that we have programmed for this project. Now I am starting the simulation. So now you can see the red LED is on, means pump is off. But now I will increase the dryness level of soil moisture sensor. Then you can see the pump is turning on, and the green LED will turn on. It means pump is on. So that's how our project will work. So this is a prototype which we made, and this is how our automation will be worked. Now I would like to hand over the presentation to Mr. Shah. Please carry on.
Thank you, Shomodi. Now I am moving on to the advantages of this system. The first and most striking advantage of this system is full automation. Once set up, it works independently. No human intervention is required. The soil moisture sensor keeps monitoring the soil continuously, and the Arduino decides when the plant actually needs water. This means that even if we forget to water our plants or we are away from home, the system takes care of everything automatically. For busy people, working professionals, or elderly individuals, this offers a huge convenience. The second advantage is efficient water usage. Traditional watering methods often waste water because we don't know how much the plant actually needs. This system uses sensors to water only when necessary and only for the required duration. It prevents over irrigation and ensures that no drop is wasted. In areas where water scarcity is a problem, this technology can make a big difference. Even in urban gardening or greenhouse setups, it promotes responsible water management, aligning with the goal of sustainable development. Another big plus is that the system is low cost and easy to build. It uses basic components like an Arduino Uno, a moisture sensor, a DC pump, and a relay module, all inexpensive and easily available. There's no need for complex hardware or high maintenance. Even beginners in electronics can assemble it and understand how it works. The simplicity of this design means it can be implemented in schools, colleges, and even by hobbyists as a learning project. This project also saves time. Once installed, it automatically takes care of watering at the right moment, freeing users from daily monitoring. For farmers and gardeners managing many plants, this saves hours of manual labor. This system is also reliable. It consistently reacts based on data and not assumptions. Whether it's day or night, weekday or holiday, the system ensures the plant always gets proper moisture. Finally, the system is scalable. You can easily expand it to multiple plants or larger fields just by adding more sensors and pumps. The code can be modified to include new features. Let's take an example like IoT monitoring, temperature sensing, or even nutrient control. So it's not limited to small home gardens. It can evolve into a smart agricultural system with minimum cost and effort. Let's now discuss the limitations because understanding them helps us improve the design further. The first limitation is that this project is currently best suited for small scale applications such as home gardens, indoor plants, or small nurseries. It works perfectly for one or a few pots, but scaling it to large agricultural fields would require multiple sensors, longer wiring, and more power. That increases complexity and cost. So, while it's a great proof of concept, large scale farming would need upgrades like wireless sensor, stronger pumps, and networked controllers to make it more practical. Next, we come to sensor sensitivity. The soil moisture census readings depend heavily on soil type and environmental condition. If we take an example, like sandy soil drains water faster than clay soil, which holds moisture longer. So, the same threshold value may not work for all kinds of soil. It has to be calibrated manually each time. Moreover, with time, sensors can get corroded or covered with minerals, reducing their accuracy. To improve this, we can use capacitive sensors instead of resistive ones, which are more stable and long lasting. The next limitation is power dependency. The system needs a continuous supply of power to operate the Arduino sensor and pump. In areas with frequent power cuts or no electricity, the system may fail to water the plants on time. One possible solution is to use battery backup or solar power, which would make it energy independent. In future upgrades, integrating a small solar panel could make the system completely sustainable and eco friendly. Another limitation is that the current design does not have precise water flow control. The pump simply turns on and off. It doesn't measure how much water is actually delivered. If the pump flow rate is too high, it may overwater. If too low, it may not reach all the parts of the plant's root. Hence, adding a flow sensor or PMW based pump control could help regulate the water quantity more accurately. This would make the system more efficient and adaptable to different plant types. Lastly, maintenance can be a small issue. The moisture sensor must be checked periodically to ensure it's working and clean. If the soil has fertilizer or high mineral content, it can affect the readings. Similarly, the pump and relay connections should be kept dry and insulated. In outdoor conditions, protection against rain, dust, and temperature changes is also important. So, regular inspection and protective casing are needed for long term use. To summarize, recognizing both sides help us design smarter, more robust system in the future. And that's what engineering is truly about, continuous improvement. Now, I am delegating the presentation to Koshani Chakraborty.
Thank you, Devnita. Now let's move on to the applications of this project, where and how the automatic plant watering system can actually be used in real life. The beauty of this system is its simplicity and adaptability. It can be used in a wide range of environments, from small homes to large agricultural setups. Firstly, home gardens and indoor plants. Many people love keeping indoor plants on balconies, in living rooms, or in offices, but due to busy schedule, they often forget to water them on time or sometimes water them too much. This system can be installed in any flower pot or small garden to ensure that each plant receives just the right amount of water. Secondly, greenhouses and nurseries. In these places, there are hundreds or even thousands of plants, and maintaining the perfect soil moisture level for each one is a big challenge. By implementing multiple automatic watering units, greenhouses can ensure uniform and precise irrigation throughout the day. This is not only saves time and labor but also helps in better yield and healthier plants. Third, agricultural fields. In many rural areas, farmers still rely on manual irrigation, which consumes time, effort, and a lot of water. By installing multiple soil moisture sensors across a farm, this system can automatically irrigate only the dry areas, ensuring water is used efficiently. This can help in precision agriculture, where every drop of water is utilized wisely. In countries like India, where water scarcity is becoming a serious issue, such automated systems can have a huge impact on saving water and increasing productivity. Fourth, IoT based smart farming system. The Arduino setup can be connected to the internet using Wi Fi or GSM modules. This allows farmers or users to monitor soil moisture remotely from their smartphones. For example, a notification can appear on your phone saying soil moisture is low, watering started. You can even view live data or control palms from anywhere in the world. Fifth, public gardens and institutions. By installing this system, water can be distributed efficiently and maintenance costs can be reduced. It also reflects on eco-friendly and tech-savvy image for institutions that adopt such automation. The future scope of this project is very exciting because it's connected to the bigger picture of smart farming, IoT, and sustainable development. Although the current system is simple and works very well, them ways can be upgraded, make it smarter, more efficient, and more user friendly. Firstly, IoT integration and remote monitoring. By adding a Wi-Fi or GSM module, the system can connect to cloud platforms like Blink, ThinkScape, or Firebase. This allows users to monitor real-time soil moisture data directly on their smartphones or computers. For example, you can open an app and instantly see whether your plants are dry or wet. You could even control the watering manually with a single tap if needed. For farmers, this means they don't have to physically check every part of their field. Data from all sensors could be collected and displayed remotely, saving both time and effort. Second, solar powered operation. Right now, it depends on an external power source like a battery or adapter. By adding a small solar panel and rechargeable battery, the system can completely off renewable energy. Thirdly, integration of multiple sensors. For example, along with the soil moisture sensor, we can use a temperature sensor to measure ambient heat, a humidity sensor to understand air moisture, and even a light sensor to track sunlight exposure. By combining all this data, the Arduino can make smarter decisions such as watering less on humid days or more during hot, dry water. And lastly, automated nutrient mixing system. Just like the plant gets water when needed, it could also receive a balanced dose of nutrients at regular intervals. Using solenoid valves and liquid nutrient tanks, the system can mix fertilizers in small amounts and supply them with the water. This could help plants grow faster and healthier while maintaining the correct balance of nutrients in the soil. Such systems are already used in advanced hydroponic farms, and integrating it with Arduino control makes it more affordable for small scale farmers too. And next, large scale implementation. By using multiple sensors connected in a wireless network, farmers could monitor and control entire fields from one central dashboard. Combining with IoT, solar energy, and automation, this could form part a smart village or smart city initiative where technology helps conserve resources and improve food production efficiently. In summarize, the automatic plant watering system is a smart, simple, and eco-friendly solution that uses Arduino technology to maintain and moisture efficiently. It helps conserve water, saves time, and ensure healthy plant growth. The best part is it's affordable and can be built easily by students. With small improvements, it can play a big role in the future of smart agriculture and sustainable living. As I like to say, technology grows where we water it wisely. Thank you all for listening patiently. I hope this project inspires you to explore how automation can make our lives greener, smarter, and better. Thank you.